Okay, so let's try this with take two. I had to step away for a moment. So my name is Cameron Owens. I am a product engineer for CoreAware Robotic Solutions. And I also do a lot of ROS development, both for Python and for C, for the robotics platforms. The real motivation for these webinars and these training videos is like myself, like a lot of engineers that are getting started with ROS. ROS can be a very difficult system to learn. And that's a combination of just how new it is, as well as a lot of the backgrounds of engineers that approach robotics. I graduated from Arizona State University with a general engineering degree with a focus on robotics, studying both mechanical and electrical engineering. And a lot of my professors at the undergraduate level really didn't know what ROS is. That's partially because of how new it is, as well as just the general knowledge of ROS that was out there. And so a huge driving factor for these tutorials is to present ROS for general engineers, both mechanical, electrical, as well as to present it to software engineers. So these first several training sessions will be primarily geared to those with not very much computer science background in approaching robotics. So this first tutorial, we're going to cover some of the very key basics of ROS, just to familiarize people with ROS, what makes it so important, and what makes it such a powerful tool. So first off, what exactly is ROS? ROS stands for the Robot Operating System. And when most people think of an operating system, the first thing that they typically think of are things like Mac OS X, or iOS, or Android, or Windows. Typically, it's something that provides a graphical user interface. Typically, most operating systems will provide you with features, things like a graphical user interface, file system management, sandboxing of your applications, hardware abstraction, and a slew of other features. Where ROS comes in is that it is much more an extension of the Ubuntu operating system and extending many of the features within Linux towards robotic-centric development. And what I mean by that is Ubuntu is the official operating system of ROS. There is a lot of really great work being done by the OSRF, as well as other organizations to extend ROS to Windows, as well as Mac OS X. Recently, I believe the OSRF announced that they have a beta version of ROS for Mac OS X. But officially, the primary operating system for ROS is Ubuntu. And so it extends the ROS or the Ubuntu operating system to do much more robot-oriented things. With ROS, the majority of the work that you're going to be doing if you do decide to go with ROS will typically be at the command line level. And so if you don't have any experience using Linux command line tools, don't be afraid. A lot of these tutorials and training sessions are designed to make you much more comfortable with using the command line. But I would recommend looking on the web or checking out other tutorials of how to get the most out of command line tools, because ROS by itself is 100% a command line tool. There are some other tools within ROS that do have a graphical component, but really all of your development and work that you do within ROS will typically be at the command line level. So don't be afraid if you don't have any Linux background. We'll be teaching some of that along the way. within future webinars, as well as ROS meetups in the Austin, Texas area. So the next thing is what are the benefits of ROS? So ROS is an open source project. It falls under the free and open source category of software. And so free and open source, the FOSS or FOSS for free and open source software is something that's really important to core-aware robotic solutions because we strongly believe in open source projects and they greatly help communities as a whole. And if you're not familiar with free and open source, what we mean is both free as in beer and free as in freedom. So what that means is free as in beer is that ROS is given away 100% free. You can go and download it as many times as you want, and you don't have to pay a penny. The other thing is free as in freedom is that you are free to use ROS in any way that you want. It's an open license under the MIT license. Excuse me. So with that, you can take chunks of ROS out and modify it, hack it, do whatever you want with it, and then redistribute it as your own software, just as long as you give credit to the work of the developers done before you. It's kind of a give credit where credit is due type of sharing community. So ROS first started out as a Stanford project, first called Switchyard in about 2007. And it wasn't until 2008 that Willow Garage, in association with Stanford, formalized Switchyard into what we know as ROS today. And so the primary developers of ROS today is the Open Source Robotics Foundation, as well as thousands of other developers. And so this is one of the other things that really makes ROS advantageous for a lot of users, is that there's such a large development base, and they're able to do that because all of the code is open source. It really accelerates a lot of development. And so rather than having to reinvent the wheel every time that you go to build a robotics application, by using open source software, you can take building blocks that are freely available and tie them together in unique and powerful ways. And so by having this large development base of people that are constantly contributing to it, it becomes better and better every day. The other main thing is that ROS provides very powerful tools. In fact, ROS provides some of the most powerful robotics tools that I'm familiar with, because one, they are robotic centric, as well as it's what the research and development communities are using. And that gives both credit to the amazing work that the OSRF is doing, as well as many other developers, as well as the importance of ROS. And so with ROS, there are tools like RViz, which is a visualization for your mapping data. There's MoveIt, which is a transformations package, be able to have your robot be able to move and do some navigation. Then there's Gazebo, which is an entire separate application by itself that goes hand in hand with ROS, that allows you to do all of your simulation. And so ROS is just it's a great and powerful tool. So next, let's start to dive into here, discussing some of the key concepts of ROS. And being able to understand these concepts will be very important. So don't be afraid to take some time and really ponder upon what these are. Especially if you don't have much in the way of a computer science background, because some of these things may be a little bit complex and difficult for you to understand. So probably one of the most powerful things of ROS is that ROS is designed to be a distributed system. And what that means is that you can run ROS on one computer locally, or you can distribute that and separate it across hundreds of, if not thousands of computers. It's very scalable. And where robotics comes into play, that's important because oftentimes we want to develop robots that are untethered, so they run off of battery power, and that navigate and do things autonomously. And both of those concepts are almost counterintuitive to each other. When you have something battery powered, computer cycles are very important to be mindful of. Like, take your cell phone, for example. When you have lots and lots of applications running on your cell phone, you can almost literally watch your battery level go down. And with a robot that's doing things autonomously, there's a lot of data and computation that is going on. By having a distributed system, what we can do is we can take a lot of that software for higher level applications and have them run on another machine that is not as power sensitive. Things like servers, desktop workstations, or even say your laptop that you can connect into power. And then you can then have your other robotic applications running on a smaller embedded system, things like a Raspberry Pi or any of the embedded Linux systems. And so what you can do is you can spread out your robotics application to lots of different machines and have them all communicating in a centralized method. And so that's kind of what we mean by a distributed system is your application can be running in lots and lots of different places to be able to accomplish one specific goal. So for example, let's build a hypothetical example of that we want to build a robotics platform that navigates autonomously within a room and does so using SLAM. SLAM standing for simultaneous localization and mapping. It's a very resource-intensive process of taking mapping data as well as image data and creating three-dimensional maps to then identify where your robot is within an environment. So with this robot, we want it to be small. We don't want it to be the size of a tank, so we can't really have a whole lot of battery power on there. But we still want to do things like image processing and other things. Well, with a small robot, we don't have a whole lot of computing power, and so we can take that video stream and that video data, and we can package it up and stream it to another computer that's much more powerful and crunch it much faster than something like a small Raspberry Pi can, and then we can ship it back. And so that's really one of the main features of ROS that I think is not really stated enough. By being able to build these distributed systems, the complexity of what you can build is almost infinite, as long as you have enough computing power behind it. The next thing that talk about is ROS core. So within, by having ROS as a distributed system, you need a name server that manages all of these things. And that's where ROS core comes in. ROS core is what ties all of the distributed system together. It's the message broker that manages all of the communication between ROS nodes. And we'll talk a little bit about what these ROS nodes are. But think of ROS core as the system as your master control system. It's what keeps track of everything that you're running within ROS. And so when you first launch your ROS applications, the first thing that you need to do is to launch ROS core. And that will allow you to run ROS services. It's basically the way that you start ROS as a whole. So the next thing that we'll talk about are ROS nodes. And so at the atomic level, all a node really is a software component or software components that do computation. So in our previous example, on the robot that navigates within a room using SLAM, we would have individual nodes for each process. So things that, so let's say our control loop for each motor. We could have each motor be their own node, or the loop as a whole could be a node. For our sensors that are collecting data, each of those would typically be a node. And then let's say that we have a robot arm on this robot. Each servo could be would be typically considered their own node as well. Nodes allow us to break software into much more manageable chunks and allow us to build very different and complex systems by tying multiple nodes together into different configurations. And what that means is it allows us to break up our software so that we're not having to write a giant application all within one text file. We can have lots of different little small C or Python programs running that share data with each other. This is important because that is a much more scalable model. It's what is used in industry. So, take a car, for example. You have wheels, you have tires, all of these are kind of standardized parts that are put together in different configurations. So think of your nodes as your individual atomic parts of building your robot at the software level. So one of the things that makes ROS so popular with research and the development community is that there are quite literally thousands of packages to drive individual nodes for building complex systems. So all that developers really have to do, a lot of the work is really writing the code that ties these nodes together. So there's a large sharing economy of authors and developers have code from everything from Arduinos to Fanuc manufacturing arms to run ROS. The next thing that we're going to talk about are ROS topics. And so we talked about nodes, and nodes are things that do computation. And I apologize, I probably should have put another slide in here talking about what ROS messages are. And so with these nodes, let's go back. So here, within these nodes, you can see how there is a node that goes down to a publication, to a topic, then to a subscription. So here in this image at the bottom is the nodes are circles and the lines are messages. And so this is how these smaller applications communicate with each other, is that they will openly publish their data via messages. And this is just how you share data, for lack of a better explanation. Well, here you can see in the middle, there's what's called a topic. And so topics, just like an online forum or a library, topics are how you organize all of these messages. And there are lots of different types of messages that you can talk about. So going back to our example of our theoretical robot system that we discussed before, of the robot that's in a room that autonomously navigates within an environment, we talked about how each sensor would be its own node, and possibly the motors would be their own node. Servos on the arm, each of those would be their own node, or even the arm itself could be a node. On our robot, let's say that we have a combination of rangefinder sensors. So, like for example, on the CoreBot CL4, we have forward-facing ultrasonics, rear-facing ultrasonic, we have IR, and in the new model that we'll be shipping later in a couple months, we're going to be including LiDAR, a LiDAR unit on there, the RP LiDAR. Each of those sensors are very similar. So with ultrasonic sensors, they take the amount of time for an ultrasonic sound to go off of the sensor, bounce off of a sound reflective object and come back, and it gives us a distance. With LiDAR, it uses a laser, same principle of timing light. But with the LiDAR unit, you have a combination of both distance as well as angle, so measured in degrees or radians. And so on this robot, we have integers that are coming in from the ultrasonics, and then we have another message coming off of the LiDAR system that has a combination of a distance and an angle. Well, the way that we can organize all of this is through topics. And I'm probably not giving a really good example of this, but we have these two different messages of just numbers, and then numbers with radians or angles. Those are numbers too, I understand, but it's a message of a different type. Well, with topics, we can publish these different types of messages. They're mapping data, and we can publish it to the same topic. So the next and last thing that we'll address is what's called the ROS graph. So we've talked about nodes, we've talked about messages, and we've talked about topics. Well, as we build our robot systems, these become exponentially more and more complex. By keeping track of all of these different processes that are running, it could become a monumental task just keeping track of, well, how many nodes do we have running on our robot? And what messages are getting published to where, et cetera, et cetera. What ROS graph does is it provides us a visual method of being able to see how our robot application is behaving. So let's look at an example with this. So here we have a ROS graph for the RP LiDAR. So here you can see all of our nodes. We have the RP LiDAR node, we have a mapping node, we have some communication nodes, we have the move node, we have this teleop node, and then we also have these topics here as well. So this is an ROS graph, and this simply just allows us to visualize how everything comes together. And this is really important, especially as your systems become much more complex, to be able to keep track of everything. So we presented a combination of things here in this webinar, which we talked about what is ROS, of how ROS is a robot operating system that's really much more of a meta operating system. It's a layer that sits on top of Linux to be able to assist you in developing robotic applications, whether that be for drones or unmanned ground vehicles or robot arms or even artificial intelligence and manufacturing, especially with ROS Industrial. Then we talked about all of the benefits of ROS, of how it's a free and open source system that gives you access to a lot of code sharing, so that you don't have to reinvent the wheel every time. And that another huge benefit of ROS is that it's one of the most powerful tools for robotics, especially if you're looking at academic research or product research and development. Then we talked about what our I forgot. We talked about the components of ROS, the key concepts, first of which ROS being a distributed system that allows you to run applications across multiple machines. And that's how the new Corobot ROS stack is that we will be announcing when we ship the first updated units of the CL4. It's designed so that your higher level applications run on a desktop workstation, and the robot is just a data acquisition system that streams data back. And this really provides you with a lot of advantages of being able to optimize your power and performance of your robot system. Next, we talked about ROS Core, how ROS Core is the name server that ties everything together and allows you to run ROS across multiple systems. Then we talked about ROS nodes. So ROS nodes, those are the atomic level of the atomic units of how ROS works. It's the sub-applications of all of your computation things. So any chunk of code that does computation, you should typically put that in its own ROS node. Then we talked about topics of how each node, it communicates some useful information out. And those messages are organized into topics. And so you can have lots of different message types going into the same topic. And the example that we discussed is using ultrasonics and IR sensors, as well as LiDAR data, to be all streamed into the same mapping topic. And those all have different data types. But then we can then organize that and package it together into a mapping message that we would then feed into another mapping node. And then lastly, we talked about the ROS graph, which is the way that you visualize all of your ROS code and how it's running. In the next tutorial, we're gonna dive a little bit more into writing our own ROS package, and then doing a little bit of simulation and starting to get yourself into developing and working on the ROS platform. I hope that this was beneficial. This was kind of the first tutorial. I apologize for any of the sound issues. We're going to be working on making those much better. If there's anything specific ROS related or robotics related, please leave a comment below. We'd love to do a webinar or training session on that. And then also subscribe and join our Google Plus page to get the latest information on upcoming webinars, as well as robotics meetups in the Austin area and possibly even Washington as well. So I hope you enjoyed it. Again, my name's Cameron Owens. If you have any questions, comments, concerns, feedback, please send that to C as in Charlie, OWENS @coreware.com. Thanks.